we're going to need to be able to, you have to go in a specific order whenever you're starting to interpret the proton NMR data. Okay, and it's a little different to interpret it than it is to interpret the C13 NMR. And so that's why it's important to make sure that you write down which of the two, why is it coming up for this? I think it's getting ready to, it may be getting ready to kick us off again. But which of the two that you're looking at? And so whenever I ask you to draw them, make sure that you write down, okay, I'm drawing proton or I'm drawing the C13. Because they do look at different things. Not only do they sit at different frequencies, but they can also answer different questions. And so we're going to be utilizing the NMR and the IR data together in order to determine and deduce the structure for unknown compounds. And so you'll be given, like, for example, maybe the chemical formula and the spectra data, and then you have to determine and draw what that is. Or I could give you the compound and ask you to draw and determine what the NMR spectrum would look like. Okay. So these are the three important things that you need to pay close attention to. First is the number of signals. Second is the integration, which is the area under the peak, which is just like from calculus. And then third is the splitting pattern, which is called multiplicity. Okay, and you've got to address them in this order. And I'm going to teach you something a little different than what the book is, because it's the way that I was taught. And especially whenever you're trying to draw the NMR spectrum. For some people it helps, some it doesn't, but so be it. And I don't have my stylus, so we're going to see how well I can draw with my fingers here. Okay, so these three pieces of information tell you three different things. Okay, so first off, let's make that smaller. Oh, whoops. Okay. Oh, come on now. Okay, the first one, for the number of signals, that tells you the number of unequal hydrogens, okay, or the number of hydrogens in different environments. I'm trying to think of a better word for the unequal. I cannot think of the word I'm looking for. But the number of unequivalent, is it unequivalent or unequivalent? Thank you. Well, if it's not, we'll make it a new word. Unequivalent. Hydrogens. Okay? Because each of those, if it's an equivalent hydrogen, it's going to be included in the same signal. Okay, so that's why different number of signals will tell you the different types of environments that the hydrogens are in. The second one technically it gives you an integer, but it's going to give you the number of hydrogens that's in that environment. Okay. That's why you have to answer these questions in this specific order, in that particular environment. I'm not really sure. I accidentally hit the... There we go. And then the third thing, the splitting pattern, it helps you with the connectivity. So far, we don't know how they're connected. We know, we may have 6 hydrogens in this one environment, 2 in this other, but we don't know how they're connected. And so the multiplicity gives you an idea of the connectivity. So it helps give the connectivity. in particular something called the J+1 rule. Some books call it the N+1, but I'll explain what that is in a little bit. But that's why you first always have to look at the number of if you're drawing this, you want to first draw the number of signals, then think about the area, and then think about the splitting pattern. I'm going to address these individually before we get going into something else. Oh, whoops. No. Let's try to... It's not wanting to let me... Well, we'll work on that later. So the number of signals first. And the best way to do this really is just to go give an example of what it means to be unequivalent or inequivalent hydrogens. And the easiest way to do that is actually has to do with naming. Because sometimes it's difficult to tell, not if it's like ethane. Well, first of all, if it's methane, there's only one type of hydrogen. Or even ethane, there's only one type of hydrogen. It's once you get to propane that you actually have two types of hydrogen. And so propane is easy enough. It's either the hydrogen is going to be on the end or it's going to be that middle carbon. But what happens if you have this really large compound? The thing of it is you can look to see if it changes the name whenever you substitute one of the hydrogens for something else. Okay, so non-equivalent there. That was the word I was looking for. Chemically non-equivalent hydrogens or protons, they're going to have a different shift than anything else because they're going to be existing in a different molecular environment. But like I said, sometimes it's kind of difficult to tell if the hydrogens are chemically equivalent or non-equivalent. So this is particularly true when people fall into the trap of just reading left to right instead of also looking up and down, or if the molecule's turned on its side, then they may not realize that, oh, these two hydrogens are the same or these two hydrogens are different. Just see. Okay, so I'm going to attempt to draw an example here. Let me see if I can make it thicker. Here we go. So first off, what molecule did I just draw? Make sure you know how to name it right now. Pentane. And so then the question becomes, how many different chemically non-equivalent hydrogens are there? How many different types? No. How many? Three. And so in pentane there are three. And so that's why I say the way to tell that is actually to first see about what would happen if you tried to substitute one of the hydrogens with, say, chlorine and then name it. So for example, if you substituted a hydrogen on this end with a chlorine, it becomes, what would its name be? 1-chloropropane. The same thing over on this end over here. If you substitute just one of these hydrogens with chlorine, it'd be 1-chloropropane. And so let me change the color because that won't help. So that means that we have one type right there. Those two carbons are equivalent to each other. Whereas if we change this one to a chlorine, what would its name be? No, I mean if it's just a single chlorine. It'd be 2-chloropropane. Likewise, the same thing happens here. So those two carbons are equivalent. If you changed, the one that I have on the right with a chlorine, it would become 2-chloropentane. However, what happens whenever we try to do and I'm hoping this is a different color. If we just instead put a chlorine on that one, that was the only one that was a chlorine, what would its name be? 3-chloro. So that's how you can tell that we have three different types of hydrogens, is the name would be different if they were substituted. Okay, so that means in this instance here, we're going to have three different peaks, three different signals, because we have three different chemically non-equivalent hydrogens. Now they're in different ratios, but they're definitely going to be non-equivalent. Okay, so that's what I mean by the number of signals. So if we look at the example that actually, I don't know how that got out of order. There's the one I thought was going to be next. Okay, so this is just showing you with propane, the same thing that I'd said before, to where if they're chemically equivalent, they're in identical environments. And so a lot of times people realize that whenever it's a nice linear thing like what we just did in here with propane. But it's a little bit more tricky whenever we start having things that are a little bit more complex. So for example, we have something like this. We're going to have many more signals, okay? And at this point in time, I wouldn't want you to try to figure that up. All right, it would definitely be a very complicated pattern. I would expect you to be able to name this one. However, I just wanted to point out a couple of things. If we look at a particular hydrogen, so if let's say that I look at this hydrogen right here, well, technically there's 3 hydrogens right there. Are there any other hydrogens that are equivalent to that one? Yes. How many total number of hydrogens are going to be equivalent? I hear 6. I heard 2. I heard 4. 5. 9. Who said 9? Who said 9? Because 9 is correct. And the reason being is each methyl has 3. There's 3 there, there's 3 there, and 3 there. So that's 9. Okay, so then if we look at this carbon, how many hydrogens does it have on it, first of all? 1. And are there any other hydrogens that are chemically equivalent to that one? No. So, because, once again, if you replace it with a chlorine, because some people then start to say, I should have used a different color, that this one right here would be similar, but in reality it's going to be a little different, because this one is hanging off of a tertiary carbon, but it's next door to this. So if you have a really good magnet NMR, it'll actually be able to tell the difference, because it's hanging next door to this quaternary carbon, whereas this one doesn't have that next door to it. So technically they're going to be different. Now, our NMR probably wouldn't be able to tell the difference because it's a smaller magnet. But if you have a really good magnet, it could differentiate between those peaks. So that's why, you just have to look to see how many. And if need be, you can do this arbitrary test group, what they say, which I just used with the chlorine. And so the next couple of slides, unless the program got them out of order, should show that. Double check. 6. Yes, it did. Okay. So here's what it's trying to show. Okay, yes, thank you. I know that. But once again, it's just showing that if you replace either one of the terminal hydrogens, or one of the terminal hydrogens, you're going to end up with the same name. They're both going to be 1-chloropropane. So those are equivalent, whereas the middle one would become 2-chloropropane. So it's going to be a different peak. So next, let's just discuss a little bit about integration. With prayer. So, Heavenly Father, I want to praise you and thank you for this day. And I ask that you reach down and undertake for us. Let us know your will for our lives and pour your spirit out upon us. In Jesus' name I pray. Amen. Yes.
You weren't recording that entire slide, and now you're recording.
That's okay.
So we got the prayer in the end.
Yes, you did. Yeah, I bet it stops whenever I change the background. Because they have the default background for white.
I have no idea what that's.
All right. We don't want to talk about that one. We now want to talk about integration. So the integration for it. So let's just go back.